So there are a number of objections to frequentist inference and hypothesis testing that are not really objections about the logic itself, but they're objections about the way that the logic and procedures can be very easily misused. So this objection has sort of a bunch of subcomponents. Just the fact that hypothesis testing logic is a little bit convoluted and it's very easy to misinterpret and misuse. So you may have studied some of these issues in other courses, other places. They're all related to each other. So the notion of p-hacking is kind of this way of going about hypothesis testing where you're trying to get a p-value that's below a certain threshold because you want to try to prove a given result. Prove in quotes because p-values don't really prove results. But you might be incentivized because the journal that you're trying to submit to really favors kind of positive research results, which would be from small p-values. And maybe your study that you're working through, you got a p-value that's right near the threshold, but it's just above the threshold, so you don't have a positive result. And then you decide, I'll remove a couple of data points that seem like maybe they could be outliers, rerun the test, and then you get a p-value that's lower than the threshold. This sort of practice is problematic. It's not within the correct frequentist logic, but it's often done and under the name of p-hacking. So the correct thing to do when you're conducting a hypothesis test is to specify the null and alternative and specify the sample size before computing the test statistic p-value and making a decision. And you're specifying the sample size up front, which blocks p-hacking, which could mess with the sample size in order to get a desired result. Another version of p-hacking is not messing with sample size, but kind of messing around with the alpha. So maybe you set alpha to be 5%, you get a p-value that's just above that 5% threshold, and you say, wait a minute, let me make alpha 10%, and now my p-value is below the threshold. That's also improper. You're not supposed to do this in hypothesis testing. You should set the alpha beforehand and then analyze your data, and it's considered p-hacking if you do otherwise. So those things are to be avoided, but they're not always avoided, and some people think the logic is just so convoluted that we should use something else, otherwise people will just be incentivized to p-hack. Multiple comparisons is another thing that you should do. Multiple comparisons often occurs, and you should adjust for multiple tests at the same time, but often people don't. So one example of this is maybe you're trying to detect what are some causes, or at least things associated with some health condition like high blood pressure, and you measure a whole bunch of different variables, how much salt and fat, carbohydrates people eat, you measure their exercise, lots of other habits, some things about their family history, to try to understand how those things might impact their blood pressure. There's lots of different tests going on, right? You're testing relationships between all those variables that I just mentioned in blood pressure. So there's multiple comparisons going on. And when you have multiple comparisons, the chance that at least one of those p-values is small and you claim a positive result is relatively high. It actually goes up with the number of tests that you have. There was a famous example of a researcher trying to kind of fool the health sciences community by doing a study with a relatively small sample size on the health effects of dark chocolate. And the researcher, conducted this. It was a real study, but it was meant to be deceiving. And he had I think 3 different groups. One he gave a larger dose of dark chocolate to, one he gave a smaller dose, and one didn't get any dark chocolate at all. And he measured lots of different outcome variables. So things like blood pressure, weight loss, other health markers. And I think there were 16 total health markers in this study. And of course, the chances that one of those relationships is a false positive, given that you're measuring so many things and there's a relatively small sample size, was really high. And he actually found out, I think, that dark chocolate was associated with weight loss. It's very likely to be a false result given how many comparisons there were, and published that result as a way of showing the community, look, your research practices are problematic. Here's a result. I'm going to publish it. And then later on, he revealed that it's very likely a false result. So all that to say, if you're not careful and you don't do multiple comparisons with adjustment, you're likely to produce problematic inferences with hypothesis testing. And then researcher degrees of freedom related to p-hacking for sure. Exploring data and then deciding, should I collect more to get a certain p-value, kind of double dipping on the data, seeing what relationships might be there and then formally testing them. Sometimes that could be problematic. A better procedure would be to split the data into an exploratory set and then a set where you actually run your hypothesis test. Excluding outliers is another possibility for researcher degrees of freedom. You decide, I want to remove some values or add in some values or something else like that. How you might group people could change your results of your test. And if you are thinking about grouping people with an eye on getting a certain result, that's another researcher degree of freedom. And there's an interesting activity that I'd like you to do before our next lesson, which is to go to this tool on the 538 blog and play around with it a little bit. So this is a tool that helps you understand what researcher degrees of freedom are in a specific example about politics. So you're allowed to change lots of different variables on the x-axis and the y-axis of a regression. And you'll see that all of those changes are researcher degrees of freedom that could make the difference between a significant result in terms of a p-value being small or an insignificant result, a p-value being high. So I encourage you to try to answer these questions here using that tool, and we'll talk about it at a future lesson.